Hi everybody, and welcome back to Digital Integrated Circuits. I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll go over Lecture 5, which is called Technology Scaling. So just a little bit of motivation, and Intel likes to put out these different illustrations and animations that are really nice for kind of showing the scale of Moore's Law and what their new processors are and what their new scaling nodes are and so forth. So in 2011, they put out this little animation or illustration that they called If Transistors Were People. And they took the Intel 4004, which came out in the beginning of the 70s, and had 2,300 transistors. And when they say how many transistors could they fit on a chip, well, it was about the average music hall capacity. Going a little further, the 286 came out in the mid 80s, and it already had 134,000 transistors on it. So that's about the capacity of a large football stadium or something like that. By the early 2000s, the Pentium 3 came out. It already had 32 million transistors on it. That's the size of the population of Tokyo. And finally, when this illustration came out in 2011, they had put out a Core i7 Extreme Edition with 1.3 billion transistors. And 1.3 billion transistors is about the population of China. Now imagine that those 1.3 billion people could fit on stage in the original music hall. That is the scale of Moore's Law. And I'll be showing many more scales of Moore's Law in this first part of the lecture. So what is the content of our lecture? We'll be discussing Moore's Law. The second part will go down into scaling models such as Dennard scaling. Then we'll go into the nanoscaled transistor, look at the secondary effects that we've discussed many of them within the manufacturing and modeling of transistors and how they've been solved over the recent past. And finally, we'll end with current and future trends in Moore's Law and transistor scaling and VLSI. So again, we're going to start now with Moore's Law. And in 1965, Gordon Moore, who was then the CEO of Intel, noted that the number of components on a chip doubled every 18 to 24 months. And he was a real prophet, so this is Gordon Moore. He made a prediction that the semiconductor technology would double its effectiveness every 18 months. That was a pretty big guess back then. So if you look over here, here's where the integrated circuit was invented, and you had something like 2 to the power of 0. So you had like one device on an integrated circuit, and a few years later you had about 8 devices or so, and it got to the point where in 1965, when he put this out, you had about 32 or 64 devices on an integrated circuit that you could fit on an integrated circuit. In this paper in the Electronics, which is a very famous and well-cited paper, he takes a economical and technological look at why he thinks that they'll be able to double the number of transistors that go onto an integrated circuit for the next 10 years, getting to 1975 when he says there'll be something like 64,000 transistors on a single die. Now, that's a pretty big prediction. I mean, that's pretty crazy to go and say 10 years from now I'll have 1,000 times the amount of the ability that I can do now. It's pretty crazy. But actually, Moore's Law continued for the next 50, maybe you could look at it, we're continuing it now, so maybe it'll be 60, maybe even more than that years. And here we see different processors that have been put out along the way. And you see from 1965, when we started, and it's been growing exponentially, as this is a log axis. So exponentially, we've been growing the number of transistors that have been put on to high-end cores throughout the years. So this is pretty amazing that it was actually kept this way. If we just look at, again, Intel type processors, so you can look throughout the years the number of transistors that have been on Intel processors, famous Intel processors, up over here till 2012. A different way to look at Moore's Law is not only the capacity that we can put on a chip, the number of devices, but actually their performance. So the calculations per second per $1,000 that you can do. So this is kind of a performance per cost. And that's kind of the essence of Moore's Law. It's an economic law. It's something that's worth doing, which we'll discuss along this lecture. Okay, so you see here, even starting from way back in around 1900, where we had like the analytical engine by Babbage that I think I showed in a previous lecture, and different types of mechanical types of electromechanical types of calculators or early computers, then going into the solid state relays, vacuum tubes, the transistor era and then the integrated circuit era, which is where we are now. And you see that there's this exponential growth of the number of calculations per $1,000 that we've been able to do for 100 years or more. So just to again emphasize the scale of Moore's law. So again, looking at Intel, Gordon Moore was the CEO of Intel, and Moore's law is a pretty important thing for Intel. It could be kind of a prophecy that invents itself, because Intel likes to kind of chase Moore's law, but it's again an economical type of thing. But let's look at the scale of this, because I don't think anything in science and engineering in the world has ever followed Moore's law in the way has followed such an exponential growth in the way that Moore's law and the capacity of integrated circuits has followed it. So imagine what would happen if other industries experienced innovation at the rate of Moore's law. In other words, doubling capacity every 2 years. And this is again something put out by Intel a number of years ago. So again, this is around 2015 or so. They say that car mileage would be so efficient now that a car could drive the equivalent distance between the Earth and Sun on a single gallon of gas. Agriculture productivity would be improved to a level that we could feed the planet on a square kilometer of land. And as for space travel, by now we could be zooming at 300 times the speed of light. And again, Stacy Smith had put this type of an illustration out of how Moore's law scale is. And Mark Twain famously said that reports of my death were greatly exaggerated when supposedly he read in the newspaper his own obituary. And the same thing could be said about Moore's law many, many times. So here's a graph that was put out by The Economist several years ago with many times that people have famously killed Moore's law, including Gordon Moore himself, who did it several times. Remember, the original Moore's law was only a 10-year law. It was from 1965 to 1975, or a 10-year prophecy or expectation. But then it was obviously expanded during the years by Moore or by others. But even Gordon Moore himself had prophesied its death many, many times. Brian Krzanich, who used to be the CEO of Intel in 2016, said, "In my 34 years in the semiconductor industry, I have witnessed the advertised death of Moore's law no less than 4 times. As we progress from 14 nanometer technology to 10 nanometer and plan for 7 and 5 nanometer, and even beyond, our plans are proof that Moore's law is alive and well." Just as a kind of a joke about this, you can see here a type of an advertisement. Computers in the future may weigh no more than 1.5 tons. And as we know, they don't weigh exactly that. A kind of a more updated thing. So Jim Keller, a superstar architect who joined Intel this year or last year, back in December, he said, "Moore's law won't be dead for at least another 30 years or so." So I guess that Moore's law is alive and well. How has Moore's law continued? Well, one of the things is technology. So if we look at this kind of not a recent plot, but something that just kind of shows how as the technology has scaled, as the feature size has gotten smaller and smaller exponentially, similar to what we see in the exponential graph. Often we call it Moore's law, even though this is not the original Moore's law. The original Moore's law, of course, was the number of transistors or devices on a chip. This is the feature size, how it has gone down over the years, and we see it's also exponential. And so we started early on with integrated circuits. They were bipolar. In the 70s, we went over to MOSFET, which were NMOS or PMOS processes, and in the 80s, we changed over to CMOS, which is what we basically use today. But different innovations have been introduced along the way, like tungsten plugs, trench isolation, copper interconnects, strained silicon, high-K metal gate, FinFETs, and so on and so on. Some of the things that we'll be discussing in the current and future trends chapter of this lecture. Yes, someday we may reach a physical limit, but we don't see that point on our horizon. I remember in 1990 when the features on the wafer were the same size as the wavelength of light. We used to print them 193 nanometers. Physics was very clear. We couldn't go any further. This is something that Stacy Smith had quoted again in the press release by Intel in 2017, showing that Moore's law was still alive, fighting with a lot of the killers of Moore's law, who are very prominently found in the press these days. And again, we still print most of our technologies with this wavelength of 193 nanometers, but we're printing 7 nanometer features with it. Recently, as I discussed with you, we've gone over to EUV, which is 13 nanometers for like the 7 plus process or the 5 nanometer processes. But again, I guess we didn't stop scaling at 193 nanometers because that was the wavelength of light. And this has been said about many different things, and these process engineers have brought ingenious innovations to overcome these limits that people thought would kill Moore's law along the way. So let's look where we are right now in 2020. If we look at Intel, one of their high core processors that recently came out, introduced in April 2020, is the Intel Core i9 10980HK. It's in a 14 nanometer process. It's a Comet Lake H architecture. It has 8 cores and 16 threads, 2.4 to 5.3 gigahertz, 12 megabytes of cache, and many billions of transistors. They don't usually put out the number of transistors anymore that they have in their processors. And if we look at the roadmap that they just recently put out in September 2019, you can see that Intel has a roadmap going from 10 nanometers, which is in production nowadays, through 7, which is coming up in the next year or so, 5, 3, 2, 1.4, and so forth. And this is the state they're in development and definition, pathfinding, or research. And you see that Intel is still on the plan of Moore's law, and of course TSMC, who's kind of bypassed Intel and leads the way, who's now already putting out chips in 5 nanometers and will be going to 3 in the next 2 years or so. They're all still on scale with Moore's law, and we don't see a real end of it in the near future. So Moore's law has many different flavors, and I just wanted to point out a few of them. And the flavors are, as I said, basically any exponential graph that we have that has to do with the semiconductor industry, we plug Moore's law in it. In fact, you can say that about all of computer science. Computer science guys will also claim that Moore's law is there, but it's not. It's actually something from the integrated circuit guys, doubling the capacity of the number of transistors or devices on a chip. But all of these things can be called Moore's law. So one of them is the evolution in memory complexity, which is a real important part of Moore's law. So if we take a pretty old graph here, you see that from 1980 to 2010, how the number of the bit capacity per chip grew exponentially, and it surpassed like an encyclopedia or 2 hours of CD audio or 30 seconds of HD TV already in 2001 or so, and it reached the human memory or human DNA in around 2007. And this has just continued, and you see here some publications from ISSCC in 2015, 16, and so forth with this vertical NAND technology, and we're getting this density that keeps growing exponentially and amazingly and giving us more and more memory capability. Amazingly, magnetic head technology, which is this graph, has also been able to continue to grow and kept our old magnetic hard disks alive and well, and we still use them even though they should have probably disappeared 30 years ago or so. One of the things that happened was to maintain Moore's law, the die size had to grow. So from the 70s until the early 2000s, die size of the Intel processors used to grow by about 14%. But in recent years, or later than that, that doesn't really apply anymore. And we saw in our scaling, in our cost models, the die size actually increases the cost of the die to the fourth. So it was by a function of to the fourth, and that's probably why the die size hasn't continued to grow. There are many chips that actually grow and continue, and they're much larger than the Intel type of cores or the high-end processors, such as FPGAs and different networking chips, and these are very expensive per die. We actually had Cerebras put out a wafer scale chip earlier this year, which was a whole wafer that was one chip. But most chips stay with a type of up to a 200 millimeter or so die size, because larger than that, the yield just drops horrendously, and the price goes up very such that it becomes a really high-end thing. Well, as we showed before in the last lecture, Moore was not always accurate. Well, it's not Moore. He didn't say that the wafer was going to continue to grow. But if we take the size of a wafer and we would have applied Moore's law to it, back in 2000, we would have already had a 57-inch wafer. So think about the size of it nowadays. Anyway, we kind of got stuck at the 300 millimeter wafer due to manufacturing problems and I guess that the companies that put out the machinery that processes wafers haven't been able to go from 300 to 450 millimeters, even though the industry would really like to. And I actually promised my daughter that I would show what I called Teman's law. So my daughter was born in 2013, and she was born in the 30th week, premature baby. And you can see my wife's hand on her. She was really, really small. And it was during a semester where I was teaching this course, and I came to the scaling class, and I put a picture of this little tiny little baby on the overhead, and everybody clapped. And I told her that every year I would put her picture on. And so you can see how she scaled up, and she's been growing every year. And this is in Purim, our type of Halloween, where she dressed up every year. And this year, finally, she got a little brother. So that's kind of a 3D integration of how Teman's law has grown. Well, I guess that Moore's law, in essence, is an economic law. And the only reason for continuously scaling and making everything smaller and continuing to integrate more and more transistors on a chip is because the cost goes down. And so it's been very important that the cost per transistor has also followed Moore's law and exponentially gone down over the years. And so you can see from 1965 until 2000 how the cost per transistor has followed this exponential graph. A few years ago, when 28 nanometers came out, there was a big scare that actually the cost per transistor was going to start to go up, and people were thinking that that may be the end of Moore's law. But if we take both data from Intel and I think from TSMC, you can see here that Intel put out the millimeter square per transistor, which keeps going down, basically the size of the transistor times the price per millimeter square, which of course goes up. We get finally we get an exponential reduction of the cost per transistor, which is continuing past even 10 to 7 nanometers and so forth. And we can also look at this type of a table that's been put out, what a basic chip area is, number of transistors that are on, and so forth. And you can see that the transistor cost per 1 billion transistors continues to go down, and it is expected to go down through 5 nanometer and 3 nanometer processes. And that's in essence a basic requirement of the continuation of scaling. Otherwise, it could be that if scaling is not economical, that will eventually kill it. So just another type of a representation of scaling. If we take this rather old figure from geek.com, we can see they showed the different Intel dies on a kind of a scaled model. So you see that this in 1971, the 4004, you can even see the part number over here. It's so big relative to the others. It was in a 10 micron process. So this was a real old process, and we got this big die. And as we continued throughout the years and got smaller and smaller, we get to over here a 16 nanometer process, which you can't even see. So that's and that's the same type of a high-end chip in a relative type of a scaling view of it. Another thing that I found that was really nice that I found on one of the blog posts over here is a Pan Am Airlines airplane where they're putting a 5 megabyte hard disk from IBM onto the airplane. Well, this thing is a 5 megabyte hard disk, whereas nowadays the guy who put out the blog post took a picture of this flash disk that was on his desk, which has a 1 terabyte on it in 2015. So that is a real type of a scale of Moore's law. Okay, so why are we doing this? And we need goals for technology scaling. And what we want to do, again, is to make things cheaper. There are different ways to look at this, but we want to sell more functions, and functions are basically transistors, more functions on a chip for the same amount of money. If we can do that, we're making things cheaper, right? We want to build the same products cheaper. So your television, your, 42-inch TV that you bought 10 years ago versus the price it is now, it's much, much cheaper nowadays. So we want to build the same products cheaper and therefore sell the same part for less money. The price of the transistor has to be reduced. But we're greedy. We also want to be faster, smaller, lower power. And you can see these different technologies that are amazingly found already quite a few years ago when this came out, in 2011, that you can find on your cell phone. Video conferencing, GPS, digital voice recorder, digital watch, 5-megapixel camera, medical library, video player, video camera, music player, encyclopedia, video game console. They're all free once we buy one of these smartphones. And the original device name is over here, what year it came out, and you see that the price, or the fixed price, is $2011. So this video conferencing would have cost you $500,000. A GPS would have cost you $300,000. So that's pretty amazing. Scaling and this integration has allowed us essentially to add all of these types of crazy things that were really expensive when they came out, free in our pockets. So this greediness, this wanting to be faster, smaller, and lower power, has driven scaling. And there's another nice way to look at this is what I call Rabbi's law of PlayStations. So Jan Rabbi, who's one of the top teachers and researchers in the field, he in his course that this course is partially based on, he discussed the fact that every year mother comes to Christmas, she wants to buy her son the next video game console, and that video game console should cost a price of $299. Well, maybe $399, but it has to be something that she can put out her money for, and she's not going to buy him the old console, she wants to buy him the new console. So here we see the PlayStation 1, the PlayStation 2, the PS3, and so forth. This is a visualization of how we think the PlayStation 5 is gonna look, and you see that despite the fact that that this machine is much more sophisticated and better than this machine, it's probably going to cost $299 or $399 because Sony has to keep it that way, or else the parents won't buy it for their kids. So this is the goal of technology scaling. In 1974, Robert Dennard of IBM came out with something he called Dennard's law, and he modeled and realized how scaling works and showed why it works economically and why it works technically. And he showed that the benefits of scaling the technology by 30% per generation will enable doubling the transistor density. And now we can see here, basically, we have the area is x times y, and if we make the area 30% lower, or like this is 0.7 of this, 0.7 squared is 0.49, that's half the area. So if we can go 30% smaller, we actually decrease the area in half. Okay, so it doubles the transistor density. It also can reduce the gate delay by 30% and thereby increase the operating frequency by 43%. We can reduce the energy per transition by 65%, which means we get a 50% power savings at a 40% increase in frequency. We also increase the die size by 14% per generation at that time to enable this, and each of these generations was about 2 to 3 years. So in the next chapter, we're going to look at Dennard's law, see how it works mathematically or scientifically, and we'll go deep into that. But before we start, I want to stop for a second and look at our Computer Hall of Fame for this week. And yes, we all have a smartphone, but I wanted to show how scaling worked for me, or at least for a lot of us who grew up with this, when we took those big computers that weighed 1.5 tons or whatever, and we got them down to the size that we had our IBM PC at home. And then really the breakthrough was when we could put a computer in our pocket. And the Palm Pilot 20 years ago was the essence of scaling, getting a computer in our pocket. And this was an amazing machine. Okay, it was known as a PDA. This was the type of machine, a personal digital assistant. This was introduced in 1996, again sold for $299. That's kind of a golden type of a price where people can buy things. It ran on a 16 megahertz Motorola Dragon Ball processor with 128K of memory. Okay, it had a 160 by 160 pixel monochrome screen, and the Pilot 1000 could store a whopping 750 addresses, 1 year of appointments, 100 to-do items, and 100 memos. So that was an amazing thing in those days. I mean, I used to have about 10 addresses on my watch, or 10 phone numbers or something like that on my cool watch that I had. But the Palm Pilot was really something else, and you could play like these black and white games. It was a great machine. It had this stylus that you could draw on it, and it came with this graffiti reference card. So if I wanted to type letters, I could just go like this, and it would understand it was an A. I could go like this, it would understand it was a B. It was kind of an initial way of digit recognition, kind of like what we do on an EnICS type of database today. And it was just a great machine. I had bought one used many years after it came out, because these things were expensive for me in those days, and I played with it for a number of years and kept my whole life on it. Okay, so that's it for this part of the lecture, and we'll continue with scaling models in the next part.